Good afternoon, everybody, and welcome to Week 4 NPTEL Previous Year Assignment Solving section. Myself, Suraj P. from Chemical Engineering Department, IIT Kharagpur. So today, most of the problems will be based on absorption. The first question is choose the incorrect statement about absorption. Absorption involves transfer of components from gas phase to liquid phase. It is used for removal of components from gas phase. Solubility in liquid phase governs the process of absorption. It is usually more favorable at high temperature. So, which of these is incorrect?
Option D.
Option D. Why it is not favorable at high temperature?
Because absorption process is a exothermic operation. So at a high temperature, the solubility of gas is low.
Okay. So yes. Solubility of gas is low at high temperature.
Kind
Hello. Can you tell?
and at a high temperature, the kinetic energy of the particles are increased, so their transfer trying to do go to another phase, so it will
Uh,
may cause a problem of solubility.
yes. It will cause yes. Like so, we can see the detailed explanation. We know that absorption is a unit operation in which solute is transferred from gas to liquid phase. It's mainly used for removal of contaminants from gas stream. We can absorb ammonia from air ammonia mixture using water. The opposite of absorption is stripping. This in stripping, the solute is transferred from liquid phase to gas phase. In most cases, stripping is followed after absorption for recovery of the solvent. Removing absorbed solid from solvent is done by stripping. The example is removal of volatile organic compound like benzene from wastewater. Like this is an example of absorption. This is the absorption tower. The process is known as amine scrubbing. Diethanolamine is used for removing H2S and CO2 from hydrocarbon mixture. So first we will pass pure amine, which is free of H2S and CO2, from the top of the tower. Then the H2S and CO2 will be soluble in amine. After that process, we will get sweet gas, which is free of H2S and CO2. So here they are regenerating the amine using distillation. Amine that is rich in H2S and CO2 is recovered using distillation. And the top product we will get H2S and CO2. From H2S and H2S we can produce sulfur in the tertiary process. So the effect of pressure on solubility. So we can see this curve. This curve is for one curve is for fixed temperature. So if we increase the pressure, the solubility will increase accordingly. This is the solubility, mole fraction of solute in liquid. This is the solubility of solute in the liquid. So curve B, it is showing that it is the SO2 is less soluble in the liquid, and curve C, which is ammonia is highly soluble in liquid water. Then effect of temperature on solubility. If we increase the temperature, then the solubility will decrease. But it is not always true. For some cases like hydrogen, nitrogen, oxygen and methane, the solubility increase with increase in temperature above 100 degrees Celsius. So absorption is performed usually at high pressure and low temperature, and stripping is performed at low pressure and high temperature. Next we can see air stripping. If we use air for removal of organic compound like benzene from water, it is known as air stripping. After air stripping, the effluent is usually treated by secondary process like carbon adsorption. Next is steam stripping. If we need to purify water benzene mixture, we will strip using steam, which is live steam, which is at high temperature. So the high temperature of steam stripping results in increase of Henry's constant. Hence, high boiling organic will be easily stripped off from water. So after stripping, it is condensed, and a phase separator is there from where we can recover the water and benzene separately. Next is natural gas stripping. It is favored for when the organic is hazardous material, and here natural gas is used for stripping contaminated wastewater with benzene. After stripping, the exist gas is passed through an incinerator for generation of heat. So it increases the fuel value of the effluent, increases the fuel value of the total process. Next we can see operating line for absorber. So this is a countercurrent absorption process. If G is the total molar flow rate of gas stream, that it contains two components, diffusing and non-diffusing, and Y is the mole fraction of diffusing solute. P bar is the partial pressure of diffusing solute. Then the mole ratio Y is given by Y by 1 minus Y, which is equal to P dash by P total minus P dash. And the molar gas flow rate of insoluble gas is given by GS. GS equal to G into 1 minus Y. Then for liquid stream, L is the total liquid stream velocity. X is the mole fraction of soluble gas in liquid stream. X is mole ratio. Then X is given by small x by 1 minus X. The material balance is expressed in mole ratio, as solvent gas and solvent liquid are essentially unchanged in quantity as they pass through the tower. Next is the material balance of absorber. So we add all the inlet. Let P be the strip that is considered for control volume analysis. So we perform the material balance in this strip, and we get this equation: GS into Y1 minus Y equal to LS into X1 minus X. So this is the equilibrium curve or solubility curve. The operating line will be above the equilibrium curve in case of absorber, but the operating line will be below the curve for stripper. The slope of operating line will be LS by GS. And next is operating line in terms of mole fraction. Like if we draw the operating line in terms of mole ratio, the plot will be a straight line, but if we draw it on the basis of mole fraction, it will be a curved line. So here the operating line is a curved line for when it is drawn in terms of mole fraction. Next one is minimum liquid to gas ratio for absorbers. Like if less liquid is to be used, then the exit liquid composition will be greater, and the driving force for diffusion will be less. So the corresponding tower height will be larger. This can be found out from the graphical method. So next is co-current flow absorber. When the gas and liquid flow in co-current, the slope of operating line will be negative. So for here we can see the operating line, which is slope is minus LS by GS. For providing exit liquid and gas in equilibrium, the absorber tower height required will be infinite in case of co-current. Co-current mode of absorption is used in two cases: when the gas to be dissolved in the liquid is a pure substance, and if rapid irreversible chemical reaction with dissolved solid occurs in the liquid, and only the equivalent theoretical stage is 1. Here the first unit is countercurrent absorption and the second unit is a co-current absorption. Next one, if G dash is the solute free molar flow rate of gas stream in absorption column, then the condition for which its value at steady state will be same throughout the entire column is that. Can you tell the answer for this? Hello.
None of the above.
No, it is not none of the above. Once more you tell. Here G dash is on solute free basis.
So, A option.
Both A and B are
Both A and B. Sorry, sir. Both A and B.
okay. So next one is absorption factor. Absorption factor is defined as like previously we have seen the operating line and equilibrium line. The slope of operating line is do you remember what was the slope of operating line for absorption?
Ratio of L by G.
Ratio of L by G, yes. Then the slope of equilibrium line is like previously we have drawn y equal to mx. So m is the slope of equilibrium line. So can you tell what is the definition for absorption factor?
B option.
B option, yes. And absorption factor is the slope of operating line to slope of equilibrium line. There are two cases when A is less than 1. The fractional absorption of solute is limited even for infinite theoretical trace. So when A should be greater than 1 for sufficient amount of absorption to occur. If A is less than 1, then we might require infinite number of trace for the absorption process. The most economical value of A is in between 1.25 to 2. And the stripping factor which is used for stripping operation, it is the inverse of absorption factor. It is a ratio of slope of equilibrium line to slope of operating line. Then type of gas or vapor liquid conducting in tray towers is dash, while in packed tower it is dash. Like in which case it is stage wise and in which case it is continuous. Can you tell the answer? In which case it is in tray tower, or what is the mode of stage wise or continuous? Hello. Hello.
In a tray tower, stage wise.
Stage wise, like why it is called stage wise each? Because each tray is considered as a equilibrium stage. So it is called so tray tower is called as stage wise and packed tower it is called as continuous. So the answer will be B. Then next question, a gas mixture is fed to an absorber at a rate of 349 kmol per hour for removal of solute using a solvent fed at rate of 120 kmol per hour. If the equilibrium relation between solute compositions in gas and liquid phase are related as y equal to 0.3x. What is the absorption factor? Can you solve this? Here L is given. L is given as 120. Liquid flow rate is 120. Gas flow rate is 349. And the slope of equilibrium line M is 0.3. So what will be the absorption factor? Can you solve and tell? Hello?
One 1.14.
Yes, 1.14, yes. Here it is written that the concentration of solute is very low in both gas and liquid phase. In that case, the flow rate of gas and liquid will remain constant and the operating line will be linear. Like the previously we have told when the operating line is drawn with respect to mole ratio, it will be linear, and in respect to mole fraction it will be curved, not non-linear. So then mole fraction will be approximately equal to mole ratio when the solute concentration is very low. So here they have given L as 120, G as 349, and slope of equilibrium line M as 0.3. So after solving this, we will get 1.15. So next one, in case of gas absorption, Kremser equation is used to find a dash when solute concentration in both gas and solvent is like why Kremser equation is used, in which case for finding a minimum solvent rate or number of stages.
Number of stages.
Yes, number of stages. And like it is used when concentration is greater than 0.5 or less than 1. Which option, A or C?
C option.
Yes, C option, yes. So here we can see the Kremser equation for absorption process. Like this is the absorption tower. Here NP represent the tray number. NP plus 1 is the vapor coming from NP plus 1 tray, and mx0 is the mole fraction of solvent. So this is the Kremser equation. We will take log on both sides and obtain NP as this one. It's for stripping also we have one Kremser equation. Here instead of absorption factor we are using stripping factor, S. So next one, a gas enters an absorber at a rate of 550 kilomole per hour with 35 mole percentage of solute and leaves with 1.5 mole percentage of solute. A regenerated solvent containing 0.2 mole percentage solute enters from top of the column. The solvent contains 89 mole percentage solute while leaving the absorption tower at bottom. Calculate minimum rate of solute free solvent required in this case. So how we can solve this, can you tell? Hello. Here they have given gas flow rate. They are asked to find minimum flow rate of liquid that is required for removing 35 mole percentage to 89 mole percentage. Can you see this whiteboard? Hello.
Yes, sir.
Okay, thank you. So here first we can draw the absorption column. Like is it legible? Can you see this?
Yes, sir.
Okay. Like here they have told the from bottom the gas is coming at rate of 550 kilomole per hour. So G will be equal to G will be equal to 550 and yn plus 1 will be equal to 0.35. And the gas leaving the absorption column, that value is given as 0.015. And the liquid that is entering the absorption column, it is having 0.002 mole fraction of gas. So x0 is and the liquid leaving the stream is having mole fraction of 0.89. First we need to convert this mole fraction in terms of mole ratio. So we know that the relation is mole fraction is equal to y equal to this mole ratio y is given as mole fraction by 1 minus y. So each case we need to find the mole ratio. So the corresponding mole ratio in feed will be yn plus 1 will be equal to 0.538. Y1 will be equal to 0.01522. X0 is equal to 0.00204. And it is to be noted that the mole ratio will be always greater than y, mole fraction, and it can take the value greater than 1 also. Then we need to find the solute free gas flow rate. Solute free gas flow rate is given by G dash. G dash equal to G into 1 minus yn plus 1. this G dash is coming to be 357.5, and we are asked to find L dash, L minimum. So first we need to do the overall material balance around this absorption columns. So we will be getting from there we know all other values except L minimum. So after solving this, we will get L minimum as 23.106. So in this problem, all the mole fractions are given and gas flow rate is given, and we are asked to find the liquid flow rate, minimum liquid flow rate. So we need to do the material balance around this absorption column, and the material balance equation will be like this: G dash into yn plus 1 plus lm into x0 equal to g into y1 plus lm into x1. From there we need to find the value of lm. All other values we know, and we are getting L minimum as 23.107. So the option will be D. So next one, did you got how to solve this? Hello?
Yes, sir.
Okay, thank you. Then next question, height of packed bed in a absorber is said. It can be estimated as, here HTP is the height equivalent of theoretical plate and NTP is number of theoretical plates. So what will be the height of absorber, packed bed absorber?
Answer B.
Answer B, yes. And next question, choose the incorrect statement among the following. Flash distillation is a single stage operation. In batch distillation, heating element in batch still must always be submerged in the liquid inside. When distillation column operates under pressure above the atmospheric pressure, there is a chance of air entry into the column through pipe fittings and joints. Separation by distillation is easier at low pressure. So which among the following is incorrect?
Option C.
Option C. Why it is wrong?
When we operate the distillation column at a vacuum, then it will be chances of entering of air through pipe fittings and joints.
Yes. So always here
Not
the
at a pressure higher than the atmospheric pressure.
okay. So the pressure will fall from atmosphere to inside the column, and like here is option D correct? Separation by distillation is easier at low pressure.
Yes, sir.
Okay. So so the answer will be C. Option C. And thank you for listening. If you have, do you have any doubts regarding this? Hello.
Sir, can you explain the solubility of gases like nitrogen, hydrogen, carbon dioxide?
Solubility. Like this one, this is an exceptional case for hydrogen, nitrogen, and oxygen. The solubility will increase with temperature for temperature above 100 degrees Celsius. So
But in fact, it's practically an exception. In most other cases, what you find that all gases, practically, I mean, almost all gases, they have reduced solubility at a higher temperature.
Thank you, sir.
Okay. Any other question or any other topic that you would like to be discussed here that we can?
Excuse me, sir.
Sure.
Sir, my question is regarding to when the solute gases are make a non-ideal solution with the solvent. In that case,
Mhm.
particularly absorption is not taken. Sir, why absorption
Okay.
is not
Okay.
taken as a
I will try to interpret your question and then try to elaborate. It's like this. For example, in many cases, it's a case of pure absorption. For example, if you're talking about, uh, say, carbon dioxide in water at a normal temperature of around, say, 32 degrees centigrade, if you increase the pressure of carbon dioxide, or rather the partial pressure of carbon dioxide, more and more amount of carbon dioxide will get into the solution. Fine. In this case also, actually what you find in your liquid phase, that is basically the carbon dioxide dissolves, immediately it forms carbonic acid and the ions dissociate. Now, what happens in many cases, there are this happens, and whenever this happens, there is an advantage because of the formation of these weak chemical bond, the solubility increases. And this is taken care of, I mean, this is taken as an advantage, particularly in cases, for example, if you would like to have removal a total amount of carbon dioxide from air. So what you do is you take a, instead of just absorbing with water, you add a little amount of alkali. For example, you make it alkaline by adding a little amount of NaOH. So what happens is the carbon dioxide will be forming sodium bicarbonate first and later on sodium carbonate. The solubility or the removal tendency will go up many times. So if, and in fact, the example which was given to you about H2S and CO2 removal from hydrocarbons by diethanol or monoethanol amine, there is a weak bond formed, and it's not exactly a physical process. There is a weak chemical bond which also forms, and that's the reason why you have a high solubility or high loading of the liquid phase. In fact, it's like this, that you'll always prefer to select a solute which forms a weak bond. Why weak bond? If you have a solute which forms a permanent, which does uh, absorb very well but forms a permanent product because of the chemical reaction, you cannot liberate the absorbed phase and absorbed component again. It takes a lot of trouble later on, possibly boiling at a much higher temperature if you have to liberate it. But if it is a weak chemical bond, for example, H2S form, for example, your CO2 forms a very weak bond with the H2O which is there. In fact, it forms carbonic acid. If you have this, you can very easily dissolve this CO2 by lowering the pressure or heating this particular CO2 loaded water and regenerate the water and reuse it. The same thing is true in case of monoethanolamine and diethanolamine. The H2S forms a weak chemical bond with the solvent, which is in the aqueous phase. It is absorbed in the absorber, and in the regenerator, it is practically boiled off. It's stripped off, or you can say that it's distilled off. So weak chemical bond formation during absorption will increase the loading of the solute in the liquid phase, that is in the solvent, many times, and at the same time it will also make it easier to regenerate the solvent by possibly boiling it off. So in fact, the choice of solute in practical situation, in most cases you will find that there is a weak bond which is formed. This is how the solutes are chosen. Perhaps now you will have one more question. Well, if there be a chemical reaction, how do you represent the actual solubility? In case of physical solubility, perhaps an equilibrium line is good enough. But if there be a reaction, yes. If there be a reaction, the reaction is not very strong. The same type of solubility curves, are equilibrium curves, are generated, and they are used for the calculations. It is basically as if the presence of reaction has improved the solubility kinetics and the solubility equilibrium also. That means the grams of the solute that can be loaded at equilibrium goes up manyfold. But the handling is exactly the same way, whether you have a reaction or you do not have a reaction. In case you have a reaction, in many cases, very strong reaction, your equilibrium line may not remain linear. But in most other cases, in case of absorption, usually a linearity of the equilibrium line is taken, and the computation becomes much easy, and basically you can find the calculations using the absorption factor, which is a very common thing to do. Anything more or anything except absorption also related thing that we can talk and discuss?
So can I ask a question about the distillation tower, if it's permissible?
Sure.
So as per lecture, we have discussed about the condensers, the partial condensers and the total condensers. So I have some questions regarding the flooded condensers. So if you can throw some lights regarding this working principle.
Flooded condenser. Okay, fine. A flooded condenser means definitely it's a condenser subcooler. Most of the time you will find that it's a horizontal heat exchanger in which some of the tubes remain submerged in the liquid which condenses. So it's not only condenses, it subcools as well. Now comes the question, that is, if it subcools, how to control it? Let's look at the role of the condenser in controlling the column top pressure. It's like this. In the condenser, which is subcooled, so quite likely most of the product which is going to be entering this condenser as feed is going to be condensed as liquid and finally leave as a subcooled liquid. That means it's a liquid at a temperature below its bubble point. Now there is one more thing which is also there. We know that ideally, or for all practical purposes, we will be condensing the condenser to be one equilibrium stage. That means the vapor present is in equilibrium with the condensing liquid. I mean, with the condensed liquid. That's the correct way to say this. So in a flooded condenser also, initially the vapor would condense to a saturated liquid at its bubble point, and as it goes out, before that coming in contact with the lower tubes, it gets subcooled and leaves. Now, in such cases, sometimes you will find, I had in one of my earlier interactions with you, I had mentioned about a column top pressure control using a hot bypass line. It is like this: a hot bypass line basically will be controlling the submergence. If you can control the submergence, quite naturally, the extent to which the liquid phase is cooled in the condenser will change. Now, there are certain columns, for example, like naphtha stabilizers, whose top product is basically a liquid which is a mixture of propane and butane, which is LPG, and there is a small quantity of non-condensable which will be leaving from the top of the condenser or from the top of the reflux drum as non-condensables. Now what happens is, the pressure in this condenser will depend. What will it be? It is supposed to be the bubble pressure of the liquid which is there. So if you have a lower temperature in your condenser, your bubble pressure will be less. And if your pressure in your condenser is less, in that case, your column top pressure is also less. So this basically, if you change the submergence by controlling the opening of your hot bypass line, which is nothing but the pressure drop across the condenser, the amount of submergence of the tubes in this condenser would change, and this would change the liquid temperature which is residing inside the condenser and its corresponding bubble point. If you have higher submergence, in that case, what you expect? You definitely will have, it's a flooded condenser. That's why you have a liquid phase residing in it. If your level is high, more number of tubes will be submerged. The cool temperature will be lower. The pressure inside, the bubble pressure inside the column naturally at a lower temperature will also be lower, and your column top, which is connected to the vapor space of the condenser, to the inlet of the condenser, that will also be lowered simultaneously. So flooded condensers are sometimes used along with a facility to control the column top pressure as well. So this is more or less about the flooded condenser, what came to my mind right now. If you really have any specific question or any additional thing to be dealt with, you can definitely write to us. You can write to Suraj, you can write to me also, or you can put a question on any topic like this in the question answer area of your course, and we'll be happy to answer those.
Sure, sir. Can I just add something to it? I need some more details to it if time is allowed.
Sure. Definitely. Let's see. We have very few people as such, so we can continue.
So with the hot vapor bypass controlling the pressure and the explanation that you gave right now, so the control valves need to be placed in both the control hot vapor bypass and the outlet of the condensers, or do we put a control valve on either of the on one of the lines? That is one of the questions. And the second question is, sir, if my knowledge is correct, the condenser in the hot vapor bypass is usually placed at a lower level than usually condensers, as in like the height of the condensers is at a lower potential, and the condenser the accumulator is at a higher potential. So how does the movement take place in this kind of arrangement? If you can put some light,
Right.
some thought to it.
Possibly you're referring to deethanizers.
So depropanize. Sorry, the propylene towers, where the propane and the propylene towers are used to separate the propane, the propylene.
Right. Basically, this you will find mostly in the light component distillate towers.
Yes,
Now,
yes, where the
yeah, because see, I have not seen the propylene towers very closely, but I have seen deethanizers, which works exactly in the same way. The deethanizers separate the ethane from from the propane, because we were requiring pure propane to be used for extraction, which should be devoid of ethane. Anyway, I'll put it like this. Uh, Normally, the pressure control system is exactly the same. At least that is what I have seen, my practical experience has shown. But the valve on the hot bypass line to control the submergence is usually fitted with a globe valve, and it is not that you manipulate it as a tool to control or regulate the pressure in a regular fashion. It is uh, kept typically say about 40% open. If I find that I require a lower pressure, perhaps I'll adjust the opening of the valve such that the submergence is more and the pressure and the temperature falls a little bit and reduces the pressure inside my condenser. I have not seen in a hot bypass line, as far as my experience goes, control valves. They are usually uh, globe valves which are operated periodically. Maybe if I have difficulty in controlling my pressure, I'll adjust the opening of it. That's what I have seen. Uh, I'll try to gather more on this. Particularly, you have talked about propylene columns. Uh, I'll find more. Definitely, I can get back to you in the next class. You're in which unit? Are you from Indian Oil or any other company?
So I work in ONGC. I work in a petrochemical sector. So here we produce the propylene. So we have a feed of a mixture of propane and propylene. So we operate the tower at 17.8 kgs, and we use water flooded condensers. So I have a particular insight, as in like curiosity, as in like how this particular exchange is actually working. So hence for the question.
Right. I'll definitely get back to you with all other details. Uh, Certainly, I will in the next class.
Thank you so much. Thank you so much, sir.
Thank you. Thank you. We still have about 5 more minutes. We can talk if you have anything specific to be discussed. Where in ONGC are you located? ONGC is such a unit I have visited only in Pata.
Sir, it's
No,
in
that was
Dahej.
Gale. Sorry. Okay, you're in the Dahej.
Gale.
Okay, Gale. Pata is Gale most probably.
Yes.
Right.
So they also have the petrochemicals units. A similar process has been performed there also. So usually
Right.
in propylene towers they have the same philosophies. So
Yeah. Yeah. In fact, if you look at the hydrocarbon distillation, which is done in different units, the basic construction of the unit and the scheme of processing is practically same. There is a little difference between the process here and the process in any other unit.
true.
Except,
But this kind
mm,
of control philosophy is gradually eradicating, which they are usually replacing with the heat pumps and all. So with the new units, the heat pumps have been put up in the columns. So I'm not able to get the much more literature with respect to this control philosophy. So I thought maybe it would be better to ask some
definitely,
guidance with your knowledge.
definitely, I'll try to get you some reference on heat pumps also. Heat pumps were not there. Like, look, I am an old man. My working has been there. Of course, I worked for a long time in industry, but at that time, at least I have not come across any heat pumps in any of the units. Mostly my experience has been limited to refineries, of course, several refineries in India. So No, I have not come across heat pumps. Definitely to make, since the energy cost has gone up tremendously, heat pumps, which was earlier considered as a showpiece and luxury, they are becoming more economic and being used more and more. Anything more from any of you, or anything you'd like to say, Suraj?
No, sir, nothing.
Nothing. Today we had only 2 external participants. Anyway, doesn't matter. I think Suraj, you take over.
Yes,
I
sir.
don't have anything else to add right now.
Yes, sir, I am leaving the meeting.
Okay. Thank you all.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you so much.
Thank you. Bye.